The most recent pictures caught by the James Webb Space Telescope have shocked researchers, giving bits of knowledge into the universe that were previously impossible. As opposed to just extending our cognizance of the universe, these pictures have uncovered a confusing reality, suggesting that our current understanding is insufficient to fully fathom the early stages of the universe's existence. The established theories concerning the origins of the universe now appear to be stretching their limits, prompting the need to examine alternative theories about its development. This raises the urgent question: how did the universe appear, and why are these discoveries presenting challenges, even for the most experienced specialists in the field of space science? It requires a deeper investigation into the true nature of the Big Bang and its ever-evolving complexities. It might now be time to re-evaluate the theory of the universe's origin itself, as its public's view has often been distorted. The Big Bang was not just an explosion inside pre-existing space. Rather, it marked the very creation of space itself, unfolding roughly 13.8 billion years ago, along with matter and time. A core idea in modern science and cosmology is the concept of a singularity, a place where gravity becomes so intense that the flow of space-time becomes infinite. Following billions of years since the universe's birth, we now understand that our cosmic home is part of a vast collaboration. For researchers, this discovery represents a crucial aspect of the universe's existence, showcasing its ongoing expansion. The universe doesn't just float into existing space, it is still growing, in contrast to conventional theories that suggested otherwise. It is believed that the first stars began to shine about 200 to 300 million years after the Big Bang, marking the end of the so-called dark age of the universe, when the first luminous celestial objects formed and evolved into galaxies. However, the speed at which these galaxies formed remains a mystery. A significant advancement occurred on July 22, when the James Webb Space Telescope released its first pictures, revealing several galaxies, some of which were already in existence about 300 million years after the universe's creation. While younger than the galaxies we see today, these early galaxies were smaller and less massive in line with the scientific models at the time. In the early universe, the matter density was too low to form galaxies as large as those we see in the current era. This discovery began with the detection of 6 prominent redshifted bright spots by the James Webb Telescope, lighting up one of the greatest cosmic mysteries. Recently, these newfound galaxies, though equivalent in age to previously identified systems, appeared nearly as large as our Milky Way. This finding has fascinated specialists in the field of Big Bang cosmology. When researchers analyzed a series of images taken by the telescope's near-infrared camera, they confirmed the presence of these distant objects. They used redshift data to verify that the light from these galaxies had traveled over 1 billion years before reaching Earth. This suggests that these galaxies existed between 570 and 700 million years after the confirmed Big Bang. This extraordinary discovery challenges conventional cosmological assumptions, which had predicted the formation of much smaller, less developed galaxies at this stage of the universe's history. Instead, the James Webb Telescope revealed galaxies nearly as large as the Milky Way, defying these expectations. The gravitationally bound stars in these galaxies had already gathered mass, surpassing 10 billion times that of the Sun. One of these galaxies even appeared to have a mass greater than 10 billion solar masses. However, whether this theory is entirely accurate is still open for debate. Regardless of whether these findings are correct, the mass in the early universe would be far greater than expected, presenting an even more complex puzzle. The discovery of these galaxies poses a significant challenge to virtually all conventional cosmological theories. Even if one of these galaxies turns out to be accurate, it would force us to reconsider our assumptions about the existence of these early cosmic structures. The matter density in the early universe would need to be far greater than initially believed. Another potential explanation is that these galaxies may have formed in ways entirely unknown to us. These discoveries raise issues that demand a reassessment of the theory of primordial cosmic evolution. Many space researchers are puzzled by these discoveries, and their concerns are often expressed in scientific publications. Those who challenge mainstream theories are frequently labeled as eccentric or extreme. However, it is clear that even those who continue to support the theory of the universe's origin face unresolved questions. Among these is the fundamental issue of how, 13.8 billion years ago, something could arise from nothing. Might something truly ever come from nothing, or was there a trigger for this event? Did it happen randomly? Stephen Hawking famously pointed out that the concept of time, as we understand it, began with the Big Bang. Therefore, This process could not have been initiated by anything else or triggered by an external cause. Similar questions arise regarding the consistency of radiation and matter throughout the universe. No matter where we look or at what distance we observe, we see a similar distribution of stars, nebulae, and radiation across the universe. Modern researchers explain this phenomenon with the theory of cosmic inflation. However, other scientists have developed this theory, suggesting that the universe expanded in a violent manner. According to this model, expansion happens solely in limited regions, like bubbles, while other areas continue to expand indefinitely. This model raises the intriguing possibility that other universes might exist within these expanding bubbles, each governed by its own set of physical laws. Such a perspective suggests that our universe may not represent the entirety of existence, but rather be part of a larger, more complex structure. Within this framework, the possibility of an eternal cycle of decay and rebirth for the universe is proposed. However, this is just one of many hypotheses in cosmology. For example, an article published in NASA's Big Deal magazine in 1955 proposed that the universe might never have had a Big Bang and may have always existed, possibly for an infinite period. In this interpretation, the universe's expansion would be absent, with the continuous development of matter giving the impression of slow progress over time. One particularly captivating theory arises from quantum physics and string theory. Some experiments have suggested that our entire universe could be a projection or simulation from a higher dimensional reality. While this may sound like the premise of a science fiction story, it connects to the Kardashev scale, which measures a civilization's ability to harness the energy of an entire galaxy. A Type 3 civilization capable of using the energy of a galaxy could potentially create an ideal recreation of a universe. However, proving the validity of such a scenario remains a formidable challenge. Investigating the depths of cosmology and the origins of the universe takes us into a realm of profound mystery and ongoing scientific inquiry. The new pictures from the James Webb Space Telescope have reignited debates about the very fabric of existence, questioning established theories and prompting researchers to reconsider core principles of how we understand the universe. Key to this conversation is the theory of the universe's origin, which forms the foundation of modern cosmology. According to this theory, around 13.8 billion years ago, the universe emerged from a dense, hot state, rapidly expanding and leading to the space-time and matter we observe today. This colossal event wasn't just an explosion in pre-existing space, it also marked the beginning of space itself. The concept of a singularity, where gravitational forces are so intense that space-time curvature becomes infinite, helps support how we understand the early universe. However, the discovery of large, mature galaxies just a few hundred million years after the Big Bang challenges conventional ideas about how quickly the first structures formed. These revelations suggest that the early universe had a far higher density of matter than previously suspected, raising questions about how such massive structures could have developed so rapidly. This compels cosmologists to reconsider how galaxies, like those observed by the James Webb Telescope, could have formed so early in the universe's history. One key theory influenced by these findings is cosmic inflation, which posits that the universe expanded dramatically in the moments following the Big Bang. This rapid expansion is thought to explain the uniformity of the cosmic microwave background radiation we see across the universe today. However, new discoveries are presenting complexities that may require adjustments to how we understand inflation. The formation of these massive early galaxies also raises important questions about dark matter and dark energy, two mysterious components that make up much of the universe's mass and energy. While dark matter is believed to provide the gravitational framework for galaxies to form, researchers still lack a clear understanding of its distribution and properties in the early universe. Because of these unresolved mysteries, theoretical physicists are exploring alternative cosmological models that challenge the standard theory of how things came to be. Some of these ideas propose that our universe could be one of many in a vast multiverse, each with its own set of physical laws and constants. These concepts, originating from string theory and quantum cosmology, suggest a far more complex and interconnected universe than previously imagined, which suggests that the universe underwent a rapid expansion in its earliest moments, not just in space but also in time. This theory, building on the concept of cosmic inflation, posits that the universe expanded exponentially from an infinitesimally small point. This expansion not only increased the physical size of the universe but also reshaped the very flow of time, making it possible for the universe to evolve into the structure we see today. The implications of this theory are profound, as it suggests that time itself may have had a beginning, and that the observable universe is just a small part of a much larger and possibly infinite cosmos. If this is true, it could mean that the universe, as we know it, is part of an ongoing cycle of creation, expansion, and eventual decay, a notion that aligns with some of the more speculative theories in cosmology, such as the concept of a multiverse. As the scientific community continues to refine its understanding of the universe's origins, the discoveries made by the James Webb Space Telescope are helping to shed light on some of the most puzzling questions in physics and cosmology. Each new image and data set brings researchers closer to answering the fundamental questions. How did the universe begin? What forces shaped its development? And are we truly seeing the entire picture, or is there more beyond what we can currently observe? Ultimately, the search for answers may lead us to rethink not only our understanding of the cosmos but also our place within it. The universe, as we continue to study it, is a vast, ever-expanding frontier, full of mysteries waiting to be uncovered. And with each new discovery, we may be one step closer to understanding the ultimate origins of everything we know. As we venture further into the cosmos, the groundbreaking data from the James Webb Space Telescope brings with it both excitement and a deeper sense of humility. The more we learn, the more we realize how little we truly understand about the vastness and complexity of the universe. Every new finding challenges the boundaries of our knowledge and forces us to confront questions that are both deeply philosophical and profoundly scientific. While the James Webb Telescope provides us with unparalleled clarity in observing distant galaxies, stars, and cosmic phenomena, the questions it raises about the universe's beginning and the fundamental forces that govern it continue to captivate researchers across disciplines. For instance, understanding the role of dark matter and dark energy, which together make up about 95% of the universe, remains one of the biggest challenges in modern science. These unseen forces, though inferred from their gravitational effects, remain elusive, with no direct detection or comprehensive explanation in sight. Furthermore, the potential existence of a multiverse, the idea that our universe might be just one of many, each with its own set of physical laws, pushes the boundaries of scientific inquiry. If true, this would completely transform our understanding of existence itself, questioning what it means for something to be real and whether our universe is just one piece of a much larger, perhaps infinite, structure. The possibility that there are other realms, with varying conditions and histories, could completely reframe how we think about our place in the cosmos. The James Webb Space Telescope's observations of the early universe also open up new possibilities for understanding the formation and evolution of galaxies. The discovery of mature galaxies only a few hundred million years after the Big Bang is one of many signs that the early universe was far more dynamic and complex than we previously imagined. These findings raise intriguing questions about the mechanisms driving galaxy formation, the distribution of matter, and the conditions that allowed such massive structures to emerge so quickly after the universe's birth.